So hello. So good evening. So shall we start? Okay. So this is what we have covered so far. We talked about the introduction. Okay. And then last time we talked about the linear regression. Okay. And classification, which are the simplest models. Okay. And then later on we will talk about today we will talk about deep networks. Okay. And so that means that you can have linear models and nonlinear models. And so last week, we also talked about how to perform model evaluation, okay, and selection. So basically, the key is that you don't want to just minimize the training error, but you want to find a model with good generalization performance. Evaluation, okay, so you can use so these are what we talked about last time. So any questions so far? No? Good. And so by the way, so towards the end of today's lecture, so we will have a short tutorial. So the TA, so Wei Yu Chen, so he will give a very brief, okay, overview on how to set up the environment, okay, such as so that you can use the Python and PyTorch tools later on, okay. And so this will also be useful for your assignments and projects. And also, yeah, so recall that this is these are what we are going to cover. Okay, so we are going to talk about this today. Okay, and oh, by the way, so there is an update on the grading scheme. Okay, so again, so recall that we have assignments. Okay, so which will include both the written and programming components. We will have a quiz. We will have we will have a final exam, okay, and then we will have project presentation, okay. Okay, yeah. So if no questions, then let's. So move on to today's lecture. Yeah, okay, so neural networks, okay. So recall that we talk about linear models, but then linear models obviously are not very powerful. So for regression, you can only use do linear regression, which is basically just a straight line. And then for classification, you use a linear classifier, then that means that you only have a hyperplane, okay, to separate the two classes. And so as we have said, so say for example, if you have two classes that are like this, then linear classifier will not give you good performance. And so that's why we need nonlinear models. Okay, so a very commonly used nonlinear models these days is the neural networks. So first I will give you an introduction to neural networks in general, and then we will talk about the very basic neural network model, okay, this whole family, starting with the perceptron, and then multilayer perceptron, and then other variants such as the CNN, recurrent net, and so on. Okay, so neural networks in fact has been around for some time. So I recall that it was started with the perceptron in the 60s, and so people in fact got interested, okay, in this kind of neural network idea quite some time back. So say for example, this is a movie, okay, Terminator 2. So how many of you have watched this movie? Just a few. Okay, so this was a 1991 movie, and then we have this guy. So of course, so this guy is Arnold Schwarzenegger. Okay, and so how is this related to neural networks? So 91, so in fact, we kind of saw a comeback, okay, started to see a comeback of the neural network. And so in the movie, they said that my CPU is a neural network processor, a learning computer. So basically, it says that, well, neural network is one machine learning model, okay. So, of course, neural networks, so we're talking about artificial neural networks. And then artificial neural networks, of course, is inspired by the biological neural networks, okay, which is the human brain. So we want to learn from the human brain because we believe that humans are intelligent, so if you want to produce intelligence behavior, okay, intelligence models, then this should be a good place to start. So although we are not biology, okay, or biologists or biology students, so we know that the human brain consists of neurons, right? So do you know how, yeah? It's not published? So you are? It's not published? Let's see. Not published. So which program are you in?
The AI program.
5103. Huh? Okay. So back to here. Okay, so we have the human brain that we want to learn from, and the human brain has a lot of neurons, and so in fact we have that many, approximately that many neurons. So that is 100 billion neurons, right? So what that means is that we do have a lot of neurons, and so this is the human brain, and the picture on the right, okay, is a picture of a simple neuron. So again, of course, we are not going to talk about the details, but it is good to see the basic structure of a biological neuron, and then we will see how the artificial neural network is related to this. And as we have so many neurons, so we know that the neurons are connected to each other, right? So on average, they have something like each neuron is connected to 1,000 other neurons. And then the idea is that so there are electrical pulses sending between the neurons, and then you see that so this is a neuron, okay, and then you have the axons, okay, and also the dendrites. And so basically what that means is that the signals will be sent through these synapses, okay, and so the signal is sent from one neuron to the other. So basically, so this is a slightly more detailed mechanism of the signal propagation mechanism. So first of all, we have these dendrites, okay, so these are basically receivers, and then so these are connected to the other neurons, and then we have the axon, okay, which is kind of the transmitter of the neural network. And then, so as you can see, so we have these axons, okay, and so at the end we have the so-called synapses, and so these are used to transmit information from one neuron and then to the other one. Okay, so these synapses are connected to the other neurons, such as here. Okay, and so the idea is so we receive, so the neuron will receive a lot of signals from the other neurons, and then they will be added together. And so if the combined signal is strong enough, okay, then they will be transmitted. So received here, and then if they are combined, if they are strong enough, they will be sent over to the axon and then to the other neurons. Okay, so the idea is we want to make something like this. Okay, so this is the artificial neural networks. So from that very brief description, so we got the idea is that so the human brain is a very complex network with a lot of neurons, and these neurons are kind of very basic, so they just combine signals and then send that to other neurons. So the key here is that we want to use a complex network with many processing elements, and each processing element corresponds to a neuron, and it's pretty simple. Okay, so that is what we meant by the basic design of a neural network. So on the left we have the biological brain, okay, with several neurons, and so on the right we have the artificial neural networks. So again, so you can see that we have a network, okay. So you see that there are units and they are connected by the edges. And so, as I said, so you have the units, okay, so these are the units, and then you have the edges, okay, which serves as the connections, and then moreover, you can see that for each connection, so there is a weight parameter, okay. So since many of you have taken machine learning or similar courses before, so how many of you have no idea of what neural network is? If all of you know, then I may just move very fast. Okay? Any objection? No? Okay, so I just move very fast. So, okay, so we have the units, the link, and the weight, okay? And then the units, so you can see, maybe you tell me, okay, the units from this diagram, so this is a very simple multi-level perceptron. And so the units are, you have the input units connected to the inputs, and then besides the input units, you also have output units, okay, which is connected to the outputs, and then you also have hidden units, okay? So they are hidden because you cannot see them from either the output side or input side, right? And by the way, so if I'm going too fast and you don't know what I'm talking about, then please interrupt me, okay? And so this is, of course you can have various numbers of hidden units, and later on we will see that you can have more hidden layers. And so you want to learn a neural network, so what does that mean? That means that you have to change something, right? Because recall that, well, on your first lecture we said that machine learning is very similar to human learning, in that you have to change, okay, with experience. So given a neural network like this, then what can be changed? So of course we can change the weight, okay, we can change the weight, okay. So, but in fact, besides changing the weight, you can also change many other things. Say, for example, you can also change the architecture. Change the architecture meaning that you can add hidden units, okay. You can add links, okay. You can remove hidden units, remove links, and so on and so on, okay. So, of course, you can learn this, or you can. So typically they are manually designed, okay, but you can also learn this, okay. So this is in the realm of automated machine learning, okay, or in the context of neural networks, this is called neural architecture search, okay, or not. But in this course, we only focus on learning the weights, okay. So neural networks, of course, has many applications. So in the very early days, people have tried to use this for autonomous vehicle. And then, so basically what that means is that you have the input from the camera, and then you go through some neural networks, and then it helps to determine the steering direction. So this was one of the first projects, okay, on applications of neural networks. This is called an LFIN. And of course, this forms the basis of autonomous driving these days. And so in the previous slide, we have a network with only one hidden layer. In general, of course, we can have more hidden layers. So say, for example, here in this network, we have 5 input units, we have 2 output units, we have 2 hidden layers, right? And so even more generally, so typically in many applications, you have more inputs. So say, for example, if you want to, in the simple case, okay, if you want to do face, okay, recognition problems, of course, typically we don't use architecture like this, okay. But then for face, okay, so the face, the inputs are, if you have a face image, then the inputs are the pixels, okay. And so the pixels can be a lot. Say, for example, you have typically your camera on your phone has millions of pixels, right? And so you can have millions of inputs here, and then you can have a lot of output units here. So back to our previous example on autonomous driving, and even if you just consider the steering direction, then you can already decide, you can already have a lot of output units. And so in this simple neural network, you have 2 hidden layers, okay, this one and this one. And we say that you can see there are lots of edges, and then recall that each edge is associated with a weight. And so you can see that even in this very simple neural network architecture, you already have a lot of parameters to learn, okay? And so multi-layer perceptron, or the picture that we have earlier, is called a feed-forward network. Feed-forward in the sense that you have the inputs here, okay, say for example at the bottom, and then you have the outputs at the top, and then the signal goes from here to there. Okay, so the signal only goes in one direction from input to output, passing through the hidden units, and so this is a feed-forward network. And of course, well, so this network has a very regular structure. Okay, so you have a 2 hidden layers, and then each hidden unit is fully connected to the, say for example, this layer of hidden units is fully connected to all the input units, and this layer of hidden units is connected to all these input units, hidden units here. So we say that this kind of architecture is called, fully connected network. Okay, fully connected. But of course, well, feed-forward network doesn't have to be fully connected. So an example is like this one. Okay, so you still have the input, but then, so say for example, this hidden unit is not connected to this one. And moreover, you can also have some connections from the input units that exit the output units. Okay, so this has some irregular connections. But still, as you can see, the signal flows in this direction. Okay, so this is still a feed-forward network. But of course, more generally, you can have other connections. You can have feedback connections. Okay, meaning that the signal does not go in one direction. So say for example here, so you have a signal going in this direction and that direction and so on, but then you go back to its own. Okay, so you can have a feedback loop. Okay, so later on we'll see how this kind of network can help in modeling the underlying task. Okay, any questions? So as I said, we will then first start with the very simple neural network. Which is the perceptron. So how many of you don't know what the perceptron is? Only one? Okay, good. So what is the perceptron? So first of all, we'll talk about the model, what is a perceptron, okay, and then we will talk about what kind of functions it can represent, the representation power, and then finally, so the perceptron is also associated with some weight, just in the other neural networks, and so we will also talk about how to learn the weights. So recall that the perceptron, well, it's a feed-forward network, okay, it is the simplest model. So recall that in general, in the network that we have seen, so we have the input, we have the hidden layer, we have the output unit, okay. And then when we talk about the simplest possible model, so that means that we want to remove something, okay, from this. Can we remove the input? So no, of course, you need some input, right? Can you remove the output? Yes or no? So no, because we are talking about, recall that in the first lecture, we said that there are 3 key machine learning paradigms, and so the first one is, the first machine learning paradigm is, supervised learning, okay, and then what is supervised learning? In supervised learning, you have a training set, okay, and then the training set contains data, so the data is in the form of input, just to make sure that you guys know what I'm talking about. So supervised learning has inputs and output, okay, so of course here we want to talk about learning the input-output behavior, so of course you cannot remove the output, right? And so that means that if you want to remove something, then you can only remove the hidden units. Okay, so this leads to the perceptron, so you have the input and the output. Okay, so this is the feed-forward, as I said, so that means that the signal goes from the input layer to the output layer. Okay, and then as you can see, so you have a lot of connections, okay, and then, so as I said, each connection, okay, is associated with a weight. So that means that there is only one layer of weight, okay, in this kind of perceptron model. And so the weights obviously are learnable, okay, because as I said, so to update or to perform neural network training, we want to update the weights. And so later on we will see that, so you also have a threshold unit, okay, as the output. And so this is the general form of a perceptron, okay, you can have a lot of inputs and then connect it to a lot of outputs. Okay, but what we argue is that, so in fact, although you have a lot of output units, but if you know how to learn, so as I said, you have to learn the weights associated with these edges. But what I argue is that if you know how to learn the weight of this perceptron with only one output, okay, then you can use the same idea to learn all the weights here. Why? So because, so what I mean is that you only need to focus on the network on the right, okay. And if you know how to do this, then you will know how to do this more complicated network with multiple outputs. So, or in other words, well, there is no extra learning difficulty associated with this network, although it has multiple outputs. So the reason is, so if you know how to learn these ways. So now the question is how to learn these ways, how to do this. So you don't know, or you don't want to answer. So how many of you don't know the answer? So how many of you don't want to answer? So all of you want to answer, but you don't know the answer? So now if you know how to do this, okay, so the network on the right, so you have one output unit and you know how to learn all the ways. So now you have this more complicated network, so how to learn the ways? So the idea is, well, although you have more ways, but then if you focus on a particular output unit, say for example this one, then you can see that, you can see what? You can see that, okay, so for this, you want to learn the weights, so that means that this network is, this output unit is only connected to the inputs by these ways, right? And so, this is exactly the same as the network on the right. Okay, or in other words, so if you look at the two different output units, okay, so this one and this one, and then you look at the corresponding set of weights, then again, you see that they share no edge or no weights in common. Okay, so that means that on the left you have 6 output units, but then you have 6 disjoint sets of parameters. Okay, so since they are disjoint, and so you can learn them one by one, and then learning one set of weights, well, you only need to know how to learn the weights of the right, of the network on the right. Okay, so that's why in the following we will only focus on the network on the right, which is called sometimes called the single perceptron. Okay, so we don't need to consider the whole network. So as I said, this is the first simplest model, okay, of in the neural network family, and so people have studied this for a long time. So in fact, there was a book called the Perceptron. Okay, he published in 1969. So by a pretty well-known AI scientist called Martin Minsky from MIT. And so next we have to describe mathematically, okay, how this works. So recall that the perceptron so tries to learn an input-output mapping. Okay, so that means that you have the inputs here, and then you have the output here. You want to specify what is the relationship between input to output. So again, I may move a bit faster. Okay, so let me know if you don't know what I'm talking about. So in general, you can have say n inputs. Okay, let's call them I1 to In, and recall that they are inspired from biological neurons. Okay, and so these can be the outputs from the other neurons. Okay, but then of course in this artificial neuron case, this can come from your image, this can come from your sensors, this can come from your feature vector. Okay, and then as I said, so you have a set of weights associated with each edge, and these weights are real numbers typically. Okay, so they can be positive, negative, or 0. Okay, so again, this is inspired from the biological case because some neurons can. So your neighboring neuron can make you more excited, and then in that case, you can treat the weights as positive. So your neighboring neuron can make you less excited, so in that case, the weights will be negative. Or your neighboring neuron may have no effect on you, and so in that case, the weight is 0. Okay. So, and then this is the equation representing the input-output behavior. So we have the inputs I1 to In. So recall this in the biological case. So all these input sources are combined together. So mathematically, well, the way to represent this is to do a simple weighted sum. Okay, so we have to do a weighted sum because, as I said, so different inputs may have different effects on their output. Okay, so each weight or each input ij has the corresponding weights wj. So you do a weighted sum, and then recall that for the biological neuron. So if the combined effect is big enough, okay, then you will be excited and then send a signal to the other neurons. So to implement this, okay, or to simulate this, so what you can do is that you compare this weighted sum with certain threshold data. Okay, so the idea is if this weighted sum is bigger than the threshold data, then you output a 1, otherwise you output a 0. Okay, so again, to implement this mathematically, you can use a step function. So what is the step functions? The step functions just looks like this. In other words, it looks as the input argument of the step function. So if the combined weight, a combined input is bigger than the threshold, then that means that this difference is positive. Okay, it's positive. So you are in this region, so that the step function will output a 1. But if this combined input is smaller than the threshold, then the difference is negative, and so the step function will output a 0. Okay, so that's how it mimics the biological neuron. Of course, biological neuron is more complicated. This is a much simplified description. Okay, but anyway, as I said, so neural networks, artificial neural networks. So the idea is that, well, I can use very simple processing elements. I just combine a lot of them, and then hopefully they will give me some interesting behavior. Okay, and so of course, so when this input argument is exactly equal to 0, okay, then it will be here, and then sometimes we will so here we define to output a 1, okay, but then sometimes we will define as 0, okay, but here we use a 1. So this is the step function, okay, so again, so this is the equation on the previous slide, and so you see that here we have the W1 up to Wn, and then the data, okay, so this makes this data looks different from the other WJs. But however, well, sometimes we don't want to make this distinction because later on we will see that WJ is for all these WJs are parameters, and this data is also a parameter. Okay, so this data parameter is in fact no different from the other WJs. So another way of kind of unifying them is to represent the data as another weight. So the way to do this is by adding an additional input, okay, which is tied to the value 1. Okay, and then so the corresponding weight on this length or edge is W0. Okay, and so we still do a weighted sum. Okay, so now instead of having D weights, or on the previous slide we have N weights, okay, so we have n plus 1. Okay, so we still do a weighted sum. Okay, so the data is subsumed in the W0 by making W0 is equal to minus data. Okay, and so you can see that's so W0 times 1 will be equal to minus data, and so you have the minus data here, so it's equal to plus data, plus W0. Okay, so this you can then simply write this way. So just be careful that the index now starts from 0. Okay, so this is nothing different from this equation. So the only advantage is that now you have WJs. Okay, and so later on we just treat the data as just another or one component in the W vector. Okay. So next we want to know how powerful is the perceptron. So recall that the perceptron is the simplest neural network model. Okay, so we want to see how good or how powerful it is. So intuitively you don't expect this to be very powerful, right? So how powerful is this? So that's why we talk about the representation power. So as the output, okay, the output is what? The output is produced by this step function, and so the possible values of O are 0 and 1. Okay, so this is binary. So obviously, so this perceptron can only implement Boolean functions. Okay, and so we want to see whether the perceptron can implement simple Boolean functions. So the simplest Boolean function is obviously the simplest Boolean functions are what? And or, right? Not? Okay, so for simplicity, we just focus on 2 inputs. Okay, so first of all, the n function, I suppose everybody knows what is the n function, right? So that means that, again, as I said, you have only 2 inputs for simplicity, x1, x2, okay, and then the n function. And so usually we use a truth table, okay, to show the behavior of this function. And so when you have 2 inputs, so how many rows are there? 4 rows, okay. So the first row is 0, 0, and then you have 0, 1, 1, 0, 1, 1. Okay, so for the n function, so this column should be what? Again, everybody should know, right? So it's equal to 0, 1, 0, 1, 0, 0, and 1. Okay, so so this is the Boolean function, and so again, you can treat this as a classification problem. So you have 4 possible input combinations, and then so 3 of them correspond to the class 0, and then 1 corresponds to the class 1. Okay, and so since this is a 2 input, 1 output function, and so if you want to use a neural network, okay, to represent this, so this neural network or this perceptron will have obviously 2 inputs, x1, x2, right, and then 1 output, which will be the n function. Agree? Okay, and then as I said before, so each edge is associated with a weight, so that means that there is a weight here, W1, W2, and you also have another weight, which corresponds to either the threshold data, okay, or if you don't like to use data, you can, just like what I said, add another input here, okay, another weight, then this is W0, and then this one is always tied to the value 1. Okay, so this is what the perceptron looks like. Okay, or if you don't like this one, then you can just use associate threshold in here. Okay, so both are equivalent. So now the question is, can it represent this n function? Okay, so can it represent this n function? So what that means is that I want to fit in the 4 rows, okay, 0, 0, 0, 1, 1, 0, 1, 1. So 4 input combinations on the left-hand side, and then I want to use that equation, step function summation minus data, okay, to produce the output. So now the question is, can you find me a set of weights, W1, W2, and data, such that by feeding in the 4 different input combinations, I can get the corresponding 4 outputs. Is it possible? So maybe I first of all give you an example on the n function. So what I argue is that if you set the weights like this, 1, 1, and threshold 1.5, then it will be able to output the n function. Okay, so we can try this out. So say for example, again, you look at 0, 0. Okay, so what is the equation of this perceptron? So recall that it is equal to step function, and then what? You do a weighted sum, okay, of the input, and so that means that the 2 weights are 1 and 1, and so that means that you have I1 plus I2, right? And then what's next? The threshold is 1.5, so you have minus 1.5. Okay, and so now you feed in 0, 0 here. Okay, and so this part will be equal to minus 1.5. Step function will give you a 0. Okay, so that's correct. Okay, and then 0, 1. So in this case, this part will be equal to minus 0.5, and so again, passing to the step function will give you a 0. So obviously 1, 0 is also 0, plus 1, 1 will give you what? So this part will then be equal to 1.5, and so step function will give you a 1. So that's why if I use this set of ways, okay, that is, I use this perceptron, I will be able to implement the n function on the last column. Is it clear? So this is the n function, okay, so that's good. Okay, n function is a simple Boolean function, and the perceptron can implement this. And so you can also visualize this. So recall that this is a classification problem, and then for classification problem, you here in this case that you have two classes, so you have a boundary, okay, separating the two classes. So now the question is, what is the decision boundary, okay, for this particular perceptron? So again, recall that. So this is we have 4 input combinations, okay, so 3 of them will give you output 0, okay, these 3 points, and then there is 1 input combination, 1, 1 will give you a 1, okay, so you have the 2 classes. And so obviously, well, intuitively, the boundary should be somewhere here, right? And so as we discussed last time, so what that means is that so this part, basically, it is the plus region, okay, and then this part is the minus region. Okay, and so what that means is that if you plug your input into this part, okay, then for the yellow region, so this number should be positive, whereas if you put in a point, okay, in the green region, so this number will be negative, okay. And so on the decision boundary, so intuitively, if you have a point falling on this decision boundary, and then you compute this value, it will be equal to 0, okay? It will be equal to 0. So the decision boundary is just this, okay? So the value in the brackets is equal to exactly 0, okay? And so in our example here, so recall that, so this is the perceptron that we have, okay? So this is the perceptron that we have, and so that means that the boundary is given by I1 plus I2 minus 1.5 is equal to 0. And obviously, well, this is the equation of a line, okay? And so recall that now we are plotting. So we are plotting, this is I1, this is I2. Okay, so for this line, the slope will be equal to what? So I suppose all of you know how to obtain the slope and intercept, right? So the slope of this line is equal to -1, and the intercept is equal to 1.5. Okay, and so that's exactly what we have here. Okay, right? And so this is the graphical visualization of the decision boundary, and so not surprisingly, it is able to separate the black dots from the white dots. Okay, so this is the n function. So of course, next one we want to talk about is the OR function. Okay, so again, everybody should know what is the OR function. So again, we consider 2 inputs. Okay, the 2 input case, again, we have the 4 combinations. And then the output of the OR function should be equal to this one. Okay, so again, so you have 2 inputs, and so that means that for the perceptron, you should have 2 inputs. Okay, so and then the associated weights are W1, W2, and then you have to find the threshold also. Okay, so 3 numbers. So again, so that means that's so you have to find the 2 weights. Okay, so these are the 2 inputs, x1, x2, and then you also have to find the threshold. Okay, so now the question is how can you suggest some numbers? 110.5. Okay, so that's it, exactly the same as the answer. So why does it work? So again, you can from this figure you can write down the mathematical equation. Okay, of this perceptron, it is equal to what? Step function, and then I1 plus I2, and then minus 0.5. Okay, so again, you can easily plug in 0, 0. So this one will be equal to minus 0.5. So the output of the step function will be 0. And if you plug in 0, 1, then this will become plus 0.5. And so this will become equal to 1, and so on. Okay, so it is easy to see that this is able to implement the n function, the OR function. Okay, and so again, this is the OR function, and so you can also write down the decision boundary. So the decision boundary is simply equal to this part, equal to 0. Okay, and so again, so if this is I1, this is I2, then the slope of this line will be equal to still -1, and then the intercept in this case will be equal to 0.5. Okay, and so diagrammatically, this is what you get. Okay, so again, you can see that you still have a two-class problem. Okay, so you have the one class here, you have the -1 class or 0 class there. Okay, and so obviously, well, as you may expect, the boundary should perfectly separate the two classes. Is it clear? And of course, by the way, so is this the only possible solution? So in other words, is it that I have to set the weights this way, 1, 1, and 1, 5? No. So can you suggest me another weights combination that also implements the OR function? Yeah, so in fact, you can easily see from this figure, right? So this is intercept is 1, 5. Okay, so from this figure, obviously, if you shift this line a little bit down, okay, to here, then it will still be able to perfectly separate the two classes. So here the intercept is 0.4, so that suggests as well this is 0.4. So this will also work. Okay, or if you like, you can also slightly change the slope of this line. So say, for example, you can use this line. No. You can use this line, right? Okay, and then it will still be able to perfectly separate the two classes. And so you can draw this line and then find out the slope and intercept and then convert that back to the equation of the perceptron. Okay, so that suggests that there are in fact an infinite number of ways to implement the n function and the OR function. Okay, so this is a very simple, right? Perceptron. So what's next? We know that the perceptron can implement the n and OR. So what else do you want to try? The lot function. Okay, so what is the lot function? So of course in this case it is a one input, right? So the lot function input is x and then output is the lot. So it's very simple. Input is 0, output is 1. Input is 1, then output is 0. Okay, in this case the structure of the perceptron will be slightly different because now you have only one input, right? And so you have a perceptron, you now only have one input, x, and so you have one w, and then you have a data, and then you want this to output the lot. So again, you have to tell me what are the values of w and data. So any suggestion? So of course, one simple solution is in the notes. So you can try -1 and -1.5. So that means that the equation is step function and then what? Minus x minus -0.5. So that is equal to +0.5, right? And so you can again plug in 0. When you have 0, then this is equal to x is equal to 0. So this is 0.5 step function over the 1. And whereas if the output is 1, then this becomes -0.5, so output is 0. Okay, so it's good. So the simple perceptron, although very simple, you can implement the and or not functions. Okay, so what else do you want to try? Yeah, so next, well, since all of you have, maybe 99% of you have taken the machine learning course at least once, okay, so you know this perceptron. The next function we want to study is the exclusive OR. So what is the exclusive OR function? So again, you have x1, x2, exclusive OR, and so you have the 4 pairs, right? So the output is 0, 1, 1, 0. Okay. So now the question is, can you find a perceptron? So again, what that means is that if you want to find a perceptron, then it will of this shape. Okay. So again, you have x1, x2. So you have to find w1, w2, and also the data threshold such that it can output the exclusive OR. Right? So now, what are the possible values of w1, w2, and data? And the answer, of course, is so all of you should know, right? So the answer is so there does not exist such a weights combination. So now the question is why? Well, maybe just that you have not tried hard enough, right? Maybe there exists some w1, w2 data combination that can implement the exclusive OR. So why do you say you cannot find this? Yeah, exactly. You can use a graph. Okay, so previously we have used a graph. Okay, we visualize this. So this is a 2-input case. So it is very easy to visualize this. So again, you can use a graph. Okay, so a picture. So this is the exclusive OR function. Okay, again, you have the 4 input combinations here, and you know that's 2 points. These 2 points will give you a 1. These 2 points will give you a 0. And then recall that if you want to use a perceptron, then the decision boundary will correspond to a. So if you use a perceptron in this case, okay, 2-dimensional case, then the decision boundary of the perceptron will always be a line, okay? And so obviously you look at this picture, so there is no way you can draw a line to separate the two classes, right? this one doesn't work, this one doesn't work, this one doesn't work, or wherever doesn't work. Okay, so obviously it doesn't work. Okay, so that's why it is not that you have not tried hard enough, but you cannot find a line to separate the black from the white. So what that means is that so the perceptron cannot separate the two classes. Okay, so that means that, well, not surprisingly, perceptron is a simple model, so it is not able to represent more complicated functions. Okay, so what that means is that in general, so a perceptron can only represent functions that are what we call linearly separable. Okay, linearly separable means that, as the name implies, that means that the two classes can only be separated by a linear boundary. So previously we have only considered the two input case. Okay, well of course we can generalize this to 3 input, 4 input, wherever, but then no matter what, so we can only implement a linear decision boundary. Okay, and so what that means is if you have a function like this, okay, so obviously this is not linearly separable, and so the perceptron will not be able to separate these two classes. Okay? So again, so that means that so if you are given a function like this, okay, you are given a training set like this, then obviously diagrammatically you can see that, so you can use a line to separate the two classes, or more generally a plane or hyperplane to separate the two classes. But whereas if you have something like this, then you cannot. Okay. But of course, well, here you cannot. But then since you know that the perceptron can implement the and function or function and not function, so if you allow the use of sufficiency, you allow the use of more perceptrons, then do you think you are able to implement the exclusive or function? So if you use more perceptrons, okay, can you implement the exclusive or function? So the answer is yes. So in fact, so some of you may know that so any Boolean function can be represented either in so-called DNF or CNF. Okay, so what is DNF or CNF? So that means that you can have a number of A and B and C and D and D wherever, and then bracket or wherever. Okay, or you can have so that means that you can have a lot of ands together. Okay, and then or and then and another thing and then so on. Okay, or any Boolean function can also be represented as a lot of or and then and then or and then and so on. Okay, and so what does that mean? So any Boolean function can be represented as and then of course some of these can have the not function. And so that means that you can break down a complicated Boolean function into and or not. Okay, and then each and or not can be implemented by a perceptron. And so by combining sufficiently many perceptrons, we will be able to implement any Boolean function. Okay, yeah?
You always just go to the linear network. If you can always get disjunctive number form, any function can be...
Any function can be represented in either DNF or CNF.
No, but isn't a two-layer perceptron enough then?
Okay, so this is a difference from this. Okay, so any Boolean function can be implemented as CNF, DNF. Okay, and so that doesn't mean that you only, but then that means that you can have a lot of layers, right? Because you can have so say for example, you can have so you can say for example, I don't know, so you can have a perceptron implementing a lot of OR wherever, and then implementing an OR, okay, and then combine this to implement AND, right? And then you can also have another of OR, and then OR, and then you can do whatever you think you like, right? So you can do something like this. Okay, you can do this. Okay, so suppose that you write down, you decompose your complicated Boolean function into a number of n or not, something like this. Okay, and then you can have some of these or not. Okay, and then you can have, and then for each n or not, you implement this by a perceptron. Okay, and then you will have some neural network structure like this. And so in this case, this does not correspond to only one single layer or two layer or whatever. Okay, it can have very irregular structure. Okay, but then this theorem. Okay, so by the way, so this is the CNF. Okay, so this is the CNF. Okay, and then this is the DNF. So as I said, so say for example, you can use one perceptron to implement this OR function. You can use another perceptron to implement this OR function, and then you can use another perceptron to implement this AND function. Okay, so you can use the 3 perceptrons to implement this function, and so on and so on. And but then what the theorem and the theorem says is that so in fact you don't need a lot of you don't need a very irregular structured perceptron. Okay, the neural network. You can just have in fact you can have just one single layer, hidden layer. Okay, but with sufficiently many neural hidden layers. Okay. So That means that one perceptron is not good enough, okay, but then you can use multiple perceptrons. So essentially, that will lead to the multi-layer perceptron that we will see later on. So coming back to this perceptron case, okay, the single perceptron. So we have seen that for the very simple in or not functions, okay, you can find the weight like this, right? Okay, so recall this for the or function. So this is a possible weight combination. But recall that this is just for the 2 input case. Okay, so now if you have 3 input, if you have 3 input, then what would that look like? So you have 3 input, then you will have W1, W2, W3, and a theta, right? If you have 1,000 input, you will have a W1000. Okay, and so you have to, so for the 2 input case, it is easy for you to manually come up with a set of weights. Okay, but then for problems in general, okay, even if it is linearly separable, then it may be hard for you to come up with the set of weights. So say for example, so this is a linearly separable problem. Okay, but if I give you this set of training samples, okay, and then ask you to find, so this is 2 inputs, right? So in principle, this will still be like a x1, x2, and so you have to find W1, W2, and theta, right? But then for this more complicated case, how to find W1, W2, and theta? So if you have this in the assignment, then what can you do? I give you this set of weights, and so can you suggest me W1, W2, and theta? So the idea is still, well, you can use, huh? No, well, we are not talking about gradient descent at this moment. Okay, so of course you can. But suppose you don't know gradient descent, okay, you just have these points, and then want to find a line like this, then what can you do?
You can just set a threshold.
Huh?
You can just try to set a threshold again.
Yeah, you can basically just draw this diagram, in fact.
Yeah.
Right? After drawing this diagram, and then you can, yeah, you see that, okay, so this line will work. And so you just find the slope and intercept of this line, and then you plug this into the equation, and then you get the weight. Right? But of course, this is 2-dimensional input, so you can still do it. 3-dimensional input, maybe a bit more trickier, right? 4-dimensional input, I don't think you can do this. Right? 10-dimensional input, definitely you cannot do it. Agree, not to mention 100, 1,000 input. So that's why, in general, we need to have a method, okay, to find the set of weights, okay, for this perceptron. Even if I tell you that the function is linearly separable. Okay? Agree? Right? So I suppose, again, so you know how to do the learning, so that's why we have to learn these functions. Okay, in other words, we have to find the weights. So how to find the weight? So recall that in supervised, we are doing supervised learning. We want to learn the mapping between the inputs and the output. Okay, and the way to do this is that we need to have a set of training samples. Okay, so we have the samples coming from the 2 classes. Say for example, I want to tell real apples from apple cartoons. Okay, then you have to tell me that these are real apples, whereas the bottom 4 pictures are not real apples. Okay, so you have the 2-class problem. And then first of all, of course, you have to somehow convert the pictures into features. Okay, of course, later on, when we talk about convolutional neural network, you can just directly input the image. Okay, but then here, assuming that you don't know CNN, right? Okay, so you have to convert each image into features. So you do feature extraction, just like what we said last time. And so say, for example, you have, at the end, suppose that you have, this is your training set. Okay, you have 6 training samples. Okay, 2-dimensional input for simplicity, and then T is the corresponding target label. So this is a 2-class problem, 0 and 1. Okay, so once you're given this training set, then just like for the N or problems, you can immediately know that the structure of the perceptron should be like this, because this is 2 inputs, okay, 1 output, okay, and then that means that's the set of weights that you have to find. The weights here, W1, W2, and theta. Okay. Or equivalency, you can also use this representation. Okay. In other words, you don't take this as theta, you just take this as one of the elements in your weight vector. Okay, you denote this by W0. So anyway, you have 3 numbers to learn. Agree? So now the question is how to learn the weights. Okay, so again, just like before, so we are going to use an iterative algorithm. So what that means is that you will go through a number of iterations. You start from somewhere, okay, and then you try and see whether you can separate the two classes. Okay, if you are very lucky, so you immediately get the solution and you are able to separate the two classes, then you are done. So otherwise, if you have misclassification error, then you have to change the weight. Okay, so this is the simple algorithm. Okay, so this is basically holds for many other neural network models later on. Okay, so the first line is initialization. Then you have an iterative procedure. Okay, and so you have to see how well your network is doing. Okay, with the current set of weights. So you look at each of the samples, compute the corresponding output. Okay, and then look at the target label from the training set, and then compare your prediction with the target. Okay, so this is what we said last time, and then use this to update the weight. Okay, and then you keep repeating this until all the samples are correctly predicted. Okay, if the function is linearly separable. So, how to update the weights? So here we give you an intuitive approach on how to do the weight update. So, as I said, you have the target. So this is the prediction. Okay, prediction is O. So observe the target is T. Okay, and so the two are different. So that means that you have an error. Okay, you make a mistake, and so you want to do some changes to the weight parameter. So what should you do? So if you look at this T minus O, so if the error is positive, so what does that mean? You should fill in this word. So what should you do? So T is the target from the training set, O is your prediction, okay, and then T minus O is positive. That means that T is bigger than O, okay. And so what do you want? So T is bigger than O, and T is something that you cannot change because it is from the training set. And so what do you want to do? You want to increase O, right? Makes sense. Okay. So how do you increase O? And so similarly, on the other hand, if the error is negative, that is T minus O is negative. Okay. So you want to decrease O. Very intuitive. Okay. So now, no matter whether you want to increase or decrease, okay, you can only do this by changing the weight. Okay. So the weight, again, recall that the weight is associated with each input. Okay. You have ij, the corresponding weight is wj. Okay. So input for a particular input unit. So it can't say input ij, it contributes wj ij, right? The weighted sum. And so if the input ij is positive, okay, and then if you increase wj, then what will happen? So the input is positive, you increase wj, so how will that affect O? You will increase O, right? But here I say that, I don't say that it will increase O, I say that it will tend to increase O. So why do I need to add the words tend to? Huh?
One of the variable increase.
No, say for example, I keep all the other, everything unchanged. Okay, same input, for all the other weights the same. I look at a particular weight, wj. Okay, then I increase wj. Am I guaranteed that O will increase? No, why not? So wj is the weight connected to ij. Okay, ij is positive, I increase wj, then O will also increase. But I cannot guarantee that. When I say tend to increase, that means that I may not be able to increase O. Why? Huh? Huh? WJ?
No, it's just that in that example is mine, looking at it, but different samples.
Again, let's still stick to a particular sample. I'm not changing the sample. I'm just talking about for this particular sample. Okay, so I have the perceptron. Okay, I have a lot of weights, and then I look at a particular weight, ij. Okay, and then this is the corresponding weight, wj. Okay, I know that ij is positive. I now increase wj, and then I have the weight at the output O. Okay, so when I increase wj, can I guarantee that O will also increase? No, why not? Yeah, exactly, because here we are talking about perceptron. Perceptron is 0 and 1. Okay, so when you increase wj, what does that mean? That means that the argument, okay, inside the step function, it will increase. Okay, but then suppose that originally the number inside the bracket is equal to minus 10. Okay, you increase wj a little bit, maybe it changes from minus 10 to minus 9. You go through the step function, what will happen? the output will still be 0. Okay, so that's why we say that it would tend to, okay. But then of course, in this example, maybe originally the number inside the bracket is equal to minus 0.1, and then you increase Wj, and then you can flip it from minus 0.1 to plus 0.2, and then the output will change from 0 to 1. Okay, so I can only say that it will tend to, okay, but of course it will not tend to decrease. Oh, agree? So this is the point. So similarly, if I look at this ij, if this ij is in fact negative, okay, so I do the same thing. So now, this time this ij is negative, I increase this wj, then what will happen to the O? So, I will tend to, so ij is negative, wj increase, so the weighted sum wj ij will become more what? So ij is negative, increase wj, so it will be wj ij will become what? More negative. Okay, and so the effect on O will be that it tend to be decrease. Okay, so say for example, originally you have a minus 2, maybe it will now become minus 3. Okay, so it will tend to decrease O. And if you are lucky, say for example, originally it is plus 0.2, and then after doing this, it will change from plus 0.2 to minus 0.5, and so you will flip the sign of the step function. Okay, so that's basically what you observe. Okay, and so now you can summarize basically all these things. So recall that, so when your prediction is the same as the target in the training set, so what should you do? How should you update the weight? Your prediction agrees with the label in the training set, so what should you do? So in the final exam, so in the midterm, or suppose in the midterm, your answer agrees with my answer, and so what penalty should you get? You don't know? Oh, that's good. Okay. So your answer agrees with my answer, and then you don't know how many marks you will get. What is the penalty you will get? 0 penalty, right? 0 penalty. Your answer is correct. 0 penalty. So 0 penalty. So that means that how much should you change your weight? Nothing, right? So you're doing okay. So no change. Okay. But then, as we said, so now we are considering the case when the target is different from the prediction. Okay, and so we have to change. So how should we change? So we argue that we should change this way. Okay, so what does that mean? So again, if P minus O is positive, and then when Ij is positive, so this part is about the change. So this part is the change, right? And so this part says that, so P minus O is positive, Ij is positive, then the change will be positive. Okay, so this agrees with this statement, meaning that I want to increase O. Okay? And whereas when this is positive, and then ij is negative, so this change will be negative. So if ij is negative, and then I decrease wj, right? And so that will tend to increase O, right? And so again, I will try to change it from 0 to 1. Okay? So basically, again, of course, you can also work out the other case. Okay, that is when the error T minus O is negative. But then you can easily see that this basically encapsulates what we want to do above. Okay, and so we also have this alpha here. Okay, so alpha is how much you want to change. Okay, so this is the learning rate for step size. So I suppose all of you know how the perceptron works. Okay, so so if you are interested in this, you can look at the demo. So again, so I think this is probably too simple for you. So you can try to update this by hand. Okay, so what that means is that you start from somewhere. Okay, in this case, you start from somewhere, and then for simplicity, you take alpha, the learning rate to be equal to 1. So all the ways start from 0, and then you look at the first pattern, and then you see whether your prediction agrees with the ground truth. If no, you use the previous equation to update W. Okay, and then you look at the second sample, again, so this is the weight, okay, and then you look at the second sample, again, compute the prediction, compare with the ground truth, and then if they agree, then as I said, you are doing okay, so you don't need to change, right? And then you look at another sample and then keep repeating. So say for example, in the third example, so you are making some error, and so again you have to change following the previous equation. So you do this for all the samples, and then this is the final weight that you get. So what should we do next? So you are done? No? Yes or no? No, because you go through the whole data set once, okay, but you have changed your weight, okay, in this epoch, and so you have to make sure that the new weights, the final weights that you obtain here, is still good for the other patterns in this training set. And so that's why you have to go through this again. So anyway, I skip. So in this simple example, we are lucky, and then we can see that. And then we can see that we have all yes here. In other words, the weight from the last epoch, okay, works for all the samples here. And then of course, in general, this may not be the case, and so you have to you have to update the weight again, and then you have to do another epoch, and so on and so on. Okay? But then if the function is linearly separable, okay, that is, the two classes can be separated by a linear boundary, then you should be able to find a weight that works for all the samples. Any questions? And so say, for example, on the data set that you have, okay, so this is the final weight solution. And again, in this two-dimensional case, so you can visualize the decision boundary. Okay, so the slope is equal to this one, and the intercept is equal to this. Okay, and then you can do a visual check in this simple two-dimensional case, and then you can see that this line can perfectly separate the two classes. Okay, so again, so this is not the unique weight vector, because obviously you can see that there exist many other lines that can perfectly separate the two classes. Okay, so that's why we have the perceptron convergence theorem, saying that, okay, if the function is linearly separable, okay, you apply the previous update equation, then it will always converge to some solution. And moreover, it will take only a finite number of steps, so that it will not go on forever. Okay, so this is the good thing. And moreover, it works for any initial choice. Okay. So now, of course, here the assumption, the big assumption is that the function is linearly separable. Okay. But what if the function, the underlying function, is in fact not linearly separable? And then if I run the perceptron update rule on this data set, then what will happen? In other words, I have a function like this. I don't know that it is not linearly separable. I just use a perceptron. I follow the perceptron update rule. Okay. And then what will happen to the learning algorithm? So what will happen? Yeah, so basically it will, it will go on forever, right? Because this is not linearly separable, so of course there does not exist a line. Okay, so it will just go, so every epoch it will have some mistakes, and so it comes with changing the weight, okay, but then obviously this is filtered. Agree? So it will fail. So good. Any questions so far? So this is the perceptron, extremely simple, right? So this is supposed to be a recap for most of you. Any questions? So if not, then let's take a break. So of 10 to 15 minutes. So of course, if you want to use only one hidden layer, you don't rely on the hidden layer.
Yeah, but hidden layer is enough to eventually be a foundation.
So there are two things. Okay, one is that any Boolean function, and the second is CNF ENF. Okay, but then you need to let the vector structure. So you just follow the graph to construct the neural network. But then another thing is that, okay, you forget about the CNF ENF, so you just use one single candidate to be able to approximate the
Even in cases where we have more complex functions, where we know that 2 layers or 3 layers are enough to be able to approximate a function that's that complex. Sometimes you find that larger, like more hidden layers, easier. No, I'm just trying to understand why do you think that is? Because
so we'll talk about this. So you're kind of you know, ahead of our schedule.
We want also to be bother you.
No. But then because we'll actually talk about that later on.
Yeah.
We'll talk about move on to another. Yeah. So the new way is right? Yeah, so it's from the start. Yeah. Yeah, from this line, just from this line. No. So the training says a 6 samples, right? 6 samples. So you are correct. So just like final exam, okay? 6 questions, okay? You did right on the second one.
So if this iteration is, you just queue.
Yeah. So you want the samples wrongly classified, okay? So want to look like and change, okay?
But we don't worry about overfitting.
No. At this point, we don't have that. Okay, we don't expect. Yeah.
That's fine. 起码它这个北京人和错位率有的话，当时给他们是大的那个，因为他回来，因为他回来了，他走，他回大不来。在马路也是个挺好的地方。其他的
Okay, so let's continue. So we have a look at what the perceptron can do, okay, and how to learn the perceptron. But then, as I said, so perceptron is limited, okay, in representation power. So you have to either combine a lot of perceptrons together, okay, or use a multi-layer perceptron, okay. So before the break, we saw that one single perceptron cannot solve the exclusive OR, and then so as we discussed, so you can combine a number of perceptrons together. So say, for example, you can use this particular neural network architecture, and then you can see that in fact it can implement the OR, exclusive OR function. So say, for example, if you input 0, 0 here, okay. So if you input 0, 0, okay, then what will happen to Y3? So Y3 will be equal to 1. So this is Y3. So 0, 0, 1, threshold is 1.5. So this is 0, and then you have 0, 0, 0, okay, with this set of weights, and the threshold is 0.5, and so the output will also be equal to 0, right? And if you change this to, say, 0, 1, then this number will become still 0, okay, but then you have 0, 0, 1, and so the combined weighted sum will be equal to what? 1, right? And so will be greater than the threshold 0.5, and so the output of this one is equal to 1. Okay, and then finally the trickiest input combination 1, 1. You have 1, 1, and then what is this? So it will be equal to 1, right? And so now you have 1, 1, 1. And so the weighted sum will be equal to 0. And so threshold 0.5, so the output is 0. Okay? So that's why if you use this combination of two perceptrons, then you can implement the exclusive OR function. Okay. So you can also interpret this as what? So you see that before you produce the actual output Y, okay, so you first use another perceptron to create an intermediate feature Y3. Okay? So that means that the perceptron does not take the raw input as input, but it will first construct some intermediate feature, okay, and then fit this to this perceptron. Okay, so this is the idea of, so you can create intermediate features, and then that will make the model more powerful. Okay, so in fact, of course, you know MLP, and then this is the idea of MLP, right? So, so MLP or multi-layer perceptron, so this is still a feed-forward network, because the input is here, output is here, and now you add back the hidden units, and so the signal still flows from here to there. Okay, still flows only in one direction, so this is still feed-forward. And so previously for the perceptron, we did not have hidden layers, and now we have add back the hidden layers. And so as I said, basically the hidden layers serves as intermediate features that you can utilize when you produce the output. Okay? And so again, so in general, the MLP can be more complicated. So here we only have one output. So this is useful when you have what kind of classification problem. So we are still talking about classification. Okay, so so this is useful when you have how many classes? 2 classes. Okay, so when you have 2 classes, you can say if the output is 0, then it's one class, and then the other is output is 1. Okay, you have 2 classes. But of course, in general, you can have more than 2 classes. And then what can you do? So everybody should know, right? For those who have taken machine learning, so you have 3 classes. Then what should you do? So instead of having 1 output unit, you can have. So the simplest solution is just to have 2 or 3, right? So you can just use 3 output units. Okay, so you use this so-called one-hot encoding, right? So if it belongs to so classes A, B, C, then so if class A, then use 1, 0, 0. Class B is 0, 1, 0. Class C is 0, 0, 1. Okay. So again, you have 1 output for each class, and so the way we do it is that, okay, we look at the, so again, so it depends on the network. Okay, so if you have a regression problem, so recall that for the perceptron, it is for classification, so we have a sign function which only outputs 0 and 1. For the multi-layer perceptron, you can also use this for regression. Okay, if you want to do a regression, that is what? So recall that the difference between regression and classification is that a regression will output so classification, you output a class label. Regression, you output a number. Okay, so if you want to output a number, then the simplest thing you can do is that you don't pass through a step function here, right? And in fact, if you remove the step function from the perceptron, then you get back standard linear regression, right? So, yeah. So, so you can say, for example, if you have multiple classes, then you can take the node output class, okay, with the largest output value, okay. So for the MLP, so it is so you have the hidden units, okay, but then we argue that the hidden units need to have some nonlinearity, okay. So if it does not have any nonlinearity, that is you just, so what that means is that you have the inputs, okay, then these hidden units just do a weighted sum, okay, and then this layer also again each unit here only performs a weighted sum. Then what will happen? So what we argue is that then using this multi-layer structure will not be useful because basically if you do a weighted sum, if you look at this, if you consider this a particular unit, okay, if you do a weighted sum, then what you are doing is basically what? So you have so the output from here is what? Summation. So say for example, if you have only 3 inputs, okay, you have W1, X1, W2, X2, plus W, for simplicity, anyway, okay, 3 inputs, okay. This one, right? Ignoring the bias, okay. So you are doing this one, right? So this output, so let's call this Z, okay, Z is equal to this, okay, right? And so this Z, you can also write this as the vector form. So in vector form means what? Just like before, or the previous. So last week, we showed that you can turn this into, say, W1, W2, W3, right? And then dot products X1, X2, X3. Okay, and so you can also write this for simplicity, just as a W dot, so this is a vector, and then X, right? Agree? And so if this is a Z1, okay, you have Z2, Z3, okay, and so Z2 is another vector, right? So let's call this, let's call it A, okay, then Z2 is another vector B, and Z3 is another vector C. Right? And so if you look at, again, use this vector form, Z1, Z2, Z3, so this is equal to what? So you can simply write this as, so this is X, okay, X1, X2, X3, and then, so what is this? This is W. So basically it is this, or maybe just write X. And then from above, okay, so this is just A transpose, B transpose, C transpose, right? And so this is, of course, a row vector. Okay, and so this is, again, you can just write this as a matrix W and then X. Agree? So what that means is that if you just do a weighted sum, okay, then the output from the first hidden layer, okay, is just a linear transform of the input. Okay, so if this is a linear transform, or maybe what we call it the first layer, okay, W1. Okay, and so similarly, so this is for the first layer, right? So if you look at the second layer, okay, so this is another, so this is basically the matrix W1, okay, and so if you look at this layer, so this should also correspond to another vector, the matrix, which is W2, okay, and so the whole output, let's call it Y, so Y is equal to what? So Y is simply equal to, first you have the X, right, you do W1 to obtain this, okay, the outputs here, and then you pass through another matrix, W2, right? And so what does that tell you? So Y is equal to W2, W1, X. And so in fact this is, so you have Y, okay, is equal to the two matrices, okay, this is W1, this is W2, okay, and then you have the X. So what is this? So you have a vector, a linear transform, another linear transform, and so this is, so this is still a linear transform, right? So you can just combine W2 and W1, and this is just another matrix, right? So two matrices multiplied together is a matrix. Okay, so that means that although it seems that you have two layers of weight, but if you just do weighted sum, then two layers of weight, you can equivalently write this as one layer with some appropriate W, which is in fact equal to this product. Okay, so that means that you have two layers. In fact, it is the same as one layer. So what if I have three layers? Three layers is W3 times W2 times W1, and so still this is a matrix. What if I have 100 layers? So you have 100 matrices multiplied together, and this is still a matrix. Okay, so what that means is that if you just do weighted sum, okay, then, well, as the name implies, this is linear transform. Okay, so linear transform of linear transform is still linear transform. Okay, so that means that if you only rely on linear elements, okay, and then no matter how hard you try, still it will be a linear transform. So that's not useful. So that means that you have to add in some nonlinearity. So because recall that all the things is based on the fact that linear models are not powerful enough. Okay, you want to have a nonlinear model. So nonlinear model, you have to add in some nonlinearity. Okay, so you cannot just have matrices. So that means that you need nonlinearities, and so you have to say, for example, compute the weighted sum, and then you have to pass this through some nonlinearity. And of course, all of you, 99% of you know that what kind of nonlinearities can be used. So you do a weighted sum, each hidden unit performs a weighted sum, and then you go through some nonlinearity. So say, for example, you pass through you don't know? Again, how many of you don't know? So if you say you don't know, I will not ask you. Okay, so how many of you don't know the answer? Okay, so how many of you don't want the answer? So do you know or not? Okay, so what are the popular nonlinear functions used in multi-level zeppelins? Say, for example, you can use the ReLU, exactly. Okay, you use ReLU. Okay, say for example. So basically, what is ReLU? Okay, so ReLU is this. Okay, so is this a linear function? No. Okay, so although it is piecewise linear, so piecewise linear is not linear. Okay, so this is not a linear function. So this is non-linear. But of course, you can use many other things. Okay, so say for example, for the perceptron, does it have some nonlinearity? So after performing the weighted sum, do you pass through some nonlinearity to produce the output for the perceptron? Yes, because you go through so after computing the weighted sum, you feed the weighted sum into step function, okay, to produce the output. So step function, this one. So is this a nonlinear function? So of course this is a is this a linear function? So of course this is not a linear function, right? So of course you can use whatever thing you like, but then we don't want to use a step function because this is not differentiable. Okay, so usually we use something which is differentiable. So that's why so in the old days, so usually people use the sigmoid function. Okay, which is just a smoothed version of the step function. And so it can be shown that for this sigmoid function, its derivative also has a nice form, okay, given by this expression. And then, of course, instead of using the sigmoid function, okay, so there is another function which is very similar to the sigmoid function. So this is the hyperbolic tangent. Okay, I suppose you have seen this in your high school. Okay, so again, as you can see, so this is very similar to the sigmoid function, except for the output range. Okay, but still it is non-linear, so you can also use this. In fact, in some neural network models that we will see later on, it also uses the hyperbolic tangent. And so in fact, you can use many other things. Okay, so there is something called the radial basis function network, or RBF network. So what it does is that, again, you have input-output. Okay, so this is the input, and this is the output. But then instead of doing a weighted sum, okay, it performs a Gaussian function. So what that means is that each unit is associated with weight, but this weight is treated as a center of a Gaussian. So I suppose you know what is a Gaussian function, right? So for the Gaussian, because it's a normal distribution, okay, so you have a mean, and then you have the variance. Okay, and so for the Gaussian function, that means that you have the signal x. Okay, and then for a particular hidden unit wj, it has this wj, which is treated as the center of the Gaussian, and so you just plug into this equation, okay, and then perform the exponential, and this gives you the Gaussian function. So the Gaussian function looks like what? So in the one-dimensional case, it looks like so basically it looks like this one, right? So in the one-dimensional case, then the center is the wj, okay, and then depending on, so basically what it performs is that depending on whether the x, the input, is close to the wj, okay, of the j hidden units. Okay, so if you are, so say for example, each of you is a hidden unit, okay, each of you holds a vector, which is the center, so if the input is close to you, then you will have a high output. If it is far away from you, then you will output a close to zero value. Okay, so again, obviously this is non-linear, and so people have also used this to construct a function approximation. Okay, so this is called the radial basis function. So this is localized in the sense that you are kind of imagine that if you are living in a two-dimensional space, okay, so the inputs are two-dimensional, and so of course the wj's is how much dimensional? If the x is two-dimensional, then the wj will also be two-dimensional. Okay, so basically that means that each unit corresponds to a position in the input space. Okay, and so again, as I said, if the input is close to wj, then it outputs a high value, otherwise it outputs a small value. Okay, so you can imagine that in the input space, so basically you will have a lot of bumps. Okay, so if you're close, then you have a big number there. If you're far away, so if you're far, so say for example, so you have two W1, W2 here. Okay, and then if your x is here, okay, then it will get a big value from this hidden unit. Okay, but if you are, say for example, close to both, okay, so say for example you are here, and then what that means is that the first hidden units will output this Gaussian, the second will output this Gaussian, and so the value here will be equal to maybe this one. Okay, so basically you are kind of superimposing a lot of Gaussians together. Okay, and so you can imagine that if you superimpose a lot of Gaussians, okay, with different weighting functions, and so you'll be able to obtain a function like this. Okay, in 1D case. Okay, so that's why people have also tried this radial basis function, and it is localized in the sense that, well, each unit will only produce output if in the local region. Okay, in other words, when you are close. When you are not close, I will output zero. Okay. So this is difference from the sigmoid function. So recall that for the sigmoid function, it looks like this one, and so that means that it will have high value even when you are far away from. You are far away. Okay, basically. So yeah, so this is what we said. Okay, so if you use the RBF, okay, then you will basically creating a lot of bumps. Oops. Okay, creating a lot of bumps. Okay, so you can imagine that by appropriately weighting these bumps, you can approximate any function. But of course, these days, well, the most commonly used nonlinear function is the ReLU function. Okay, so mathematically, it is just given by this max function. Okay, so as I said, this is nonlinear, and so it may not be very clear. So on this part, it is 0. Okay, so this is straight line. So it is the most popular, and as you can see, so since you have just 2 straight line segments, so the computation is very easy. Okay, unlike the sigmoid function. So recall that so some of you may know what is the form of the sigmoid function. So sigmoid function is equal to what? In fact, it is equal to 1 over 1 plus e minus x. Okay, so of course, but it is not too complicated, but still, if you compare this with the ReLU, okay, the sigmoid function involves computing the exponential, which is obviously much more expensive than doing this ReLU function. And so this is efficient, and of course, the gradient is also simple. So recall that for the sigmoid function, the gradient is given by this equation. Okay, so you're given this equation. So this equation is not too complicated, but if you can compare with the ReLU is even simpler, because what it says is that if you are here, then the gradient is equal to 1. If you are in here, then the gradient is 0. So it's very simple, right? So basically, you don't need any computation at all. Okay, so that's why it's very commonly used. And moreover, it has sparse activation. Okay, so meaning that so you can output 0 or 1, 0 or none. So oftentimes it will output 0. Okay, so 0, then that means that so that unit is kind of turned off. But of course, well, the gradients can be 0. So as I said, the gradient here for this part is 0. And so sometimes, so when we want to use gradient descent, okay, recall the last time we use gradient descent to train our linear models. Okay, and then again, recall that so we have to define a loss function. Okay, and then so when would that be problematic? So sometimes it is problematic. So when you have when you want to do linear classification, and then you pick the simplest loss function, which is the 0, 1 loss. Okay, and then what you get is that most of the time the gradient is 0. Okay, gradient is 0, meaning that you don't know how to change the weight parameters. So 0 gradient is sometimes 0. So for the ReLU, sometimes you also have 0 gradients. So oftentimes that is not a big problem, but if you really want to avoid this, then some people have tried to, well, kind of slightly change this to a little more slope. Okay. But anyway, so the ReLU usually works pretty well. And you also have the universal approximation. Okay. So just like what we said before, so it can be shown that if you have the input, you have the output, okay, and then you have one hidden layer, okay, of sigmoid units, and then provided that you have a sufficiently large number of sigmoid units, then this network, okay, x and then say fx, so this network is able to approximate any function, okay, as close as you like. Yeah?
For the ReLU function, can you explain what is the benefit of just getting rid of the negative? Because we are getting the max.
Oh, okay. So you mean this red line?
Yeah.
So the point is that so sometimes when your input is to the ReLU is when your input to the ReLU is here, okay, then so the function is output is 0, okay, and then you do the gradient, right? When you want to do gradient descent, and then the gradient is again 0, right?
But why we get rid of the negative? Like,
Yeah. So the point is that when the gradient is 0, then you cannot perform any weight change. Okay. So that's why sometimes we want to avoid having 0 gradients. So how to obtain 0 gradients? So 0 gradient means it's flat. Okay. So I just don't want it to be flat. So that's why you can slightly tilt this a little bit. Okay. And so you will have a slight non-zero gradient, even when you are on the left side of the axis. Okay. And then you can still have a little bit of gradient information to update. Okay. So this is called the lect3 value. Okay. Okay. But oftentimes just using the ReLU is okay. Any other questions? So we have the universal approximation property, meaning that while you use one layer of hidden units, okay, then you'll be able to approximate any function, okay, to any precision. So this is an intuition, okay, for the sigmoid function, but based on 2 hidden layers, okay. So what it says is that so this is not one layer, one hidden layer, it is 2 hidden layers, okay. So when you have 2 hidden layers, so obviously, when you have one hidden layer is good enough to approximate any function, then 2 hidden layers is, again, obviously also good to approximate any function, right? So why is it that 2 layers can give you a good approximation? So the idea is, well, you have 2 inputs here, and then you have the sigmoid function. So the sigmoid function essentially is performing So what is the sigmoid function? So essentially it is performing kind of this function here. Okay, so imagine that you are doing this two-dimensional input space. Okay, so by changing the weight parameters, you may obtain this sigmoid function or that function or whatever. Okay, or this, right? So the idea is, so think about this. So if you have 4 such sigmoid units, okay, so one in this direction, the other in this one, and then the other in this one, and this one. And so when you combine all these, so this is what this first layer weight is doing, create these 4 hidden units. Okay, and then you have another layer, okay, which adds all these outputs together, then what will you get? So when you have these 4 sigmoid outputs added together, so what do you get? You have this, plus this, plus this, plus this, right? So what do you get? So basically you get something on the top. Right? And so what that means is that it is kind of like, so if you have 4 such sigmoid units, then it is basically kind of like a RBF unit. Okay, and so again, as I said, so if you can create a BOM, okay, and then you want to approximate, so in this case, function with 2-dimensional input, okay, and so in that case, that means the function is something like that, and then you want to create a BOM here, a BOM there, and so on and so on. So now you can create a BOM here, and then of course you can change the positions of the sigmoids, and then you can create another BOM there, and so on and so on. So by adding all these BOM together, so this is for creating a particular BOM, and then you can have another layer here, right? Takes all these together, and then you will be able to combine all these together. Agree? So this is basically the idea why you don't need a lot of layers. Okay, but then of course, well, just like desk students asked before the break. Okay, so if you have one hidden layer, okay, it's good enough for universal approximation. So why do you need 2 hidden layers, or more hidden layers, or deep networks in general? So deep network is basically neural network with a lot of hidden layers. Okay, so why do you need so many hidden layers? And so the answer is, so in terms of representation power, okay, so that will not give you extra representation power. Okay, but then, first of all, of course, if you have more than 1 hidden layer, then of course it will still be universal approximator, right? So which is obvious. But then, why do we need more? So because maybe you are able to use a smaller network. So the idea is, well, so you can just imagine that. So you have this is the input, and then you create a sigmoid unit or whatever unit here, right? And then you have these, and then based on these, you create another sigmoid or ReLU, okay, and so on. And so as you go up and up, so what will happen? So at the first layer, so they are basically, say, for example, sigmoid, okay. So at the first layer, all these functions are just sigmoid units, okay. And so we argued that, okay, if you have a sufficiently large number of sigmoid units, you will be able to approximate any function. Okay, so that means that in the one-dimensional case, suppose that you have a sigmoid like this, and then you have another sigmoid, I don't know, like this, and then whatever, okay, and then you have some other sigmoids, okay, like this. And so when you add them together, you can create possibly a complicated function, right? But you obtain the final output by just combining sigmoids. And then intuitively, if the function is very complicated, you may need a lot of sigmoids. Okay, but then if you use a multi-layer structure, then what will happen? So at the first layer, it is a sigmoid function, and then you have lots of sigmoid functions, and then you combine these sigmoid functions together, so that function will be intuitively more complicated than a sigmoid function, right? So, and then if you have these more complicated functions, and then also combine them together, so that will be an even more complicated function, right? So that means that if you build a deep network, okay, you can easily create very complicated feature extractors, okay, or intermediate features. So recall that the idea of having hidden units is just to create intermediate features so that I can use this to produce my output. Okay, so if your output is based on combining simple ingredients such as the sigmoid function, you may need a lot. But if you can create very complicated functions as your intermediate features, then it's likely that you may need fewer units, right? Okay, so if you need fewer units, then what's the advantage? So you use a deep network, maybe you don't need to use 10,000 hidden units. Okay, so what's the advantage of doing this? So again, so you have fewer units. Okay, so each units will need some computation. Okay, so you use fewer units means that you have fewer computation and also fewer storage, right? And then besides all this, so recall that you have fewer units means that you have fewer number of weights, and so on. So what's the advantage of having fewer weights in a model? So if you have a lot of weights, so where did the weights come from? So how to obtain the weights? Yeah, backpropagation, but then you need some information, right, to obtain the weights. Okay, so where does the information come from? Yeah, calculate the gradient, but then on a more abstract level, okay, you do gradient descent, so there's a mechanism to produce the weight update. Okay, but then intuitively, so you want to learn the weight, and so where does the information come from? From the training data, right? Okay, so now the point is if you have more parameters, you need to learn more, then you need more data. Okay, so that's why, okay, so if you want to make it more data efficient, okay, then you try to reduce the number of weights, okay, and so it is better to do a deep network instead of a shallow network. Okay? So how to determine the network structure? So of course, well, this is a very complicated problem. Okay, so as I said, well, you can use techniques like a neural architecture search. Okay, but then so this is more complicated, and usually, okay, so you have to do a little bit of experience, okay, and a little bit of trial and error. Okay, so any other questions? So then, oops. So we have a lot of weights, okay? So you have the structure, you have the network, and then you have a lot of weights. And so the question, of course, is that you have to learn the weights, okay? So for the perceptron, we have the perceptron update rule. And then for the MLP, so obviously MLP is more complicated than the perceptron because, so first of all, you have the nonlinear activation, okay? So you have a lot of sigmoids or Gaussians or Renews, okay? And then moreover, you have multiple layers, okay? So that means that you will need more complicated learning algorithms. So how to do this? Well, still basically these days we are still using gradient descent. Okay, so recall that gradient descent is, again, you start from somewhere, and then it's the current W, okay, you compute of course you have to define the loss function, and then you compute the gradient of the loss function with respect to the current W, okay, and then you have the gradient direction, okay, so recall that the gradient will tell you which direction will best increase the loss, okay, increase the objective. But now you don't want to increase the loss, right? So you want to decrease the loss. So if the gradient is in this direction, and then you will move in the other direction. Okay, so that's why you have the W in the mathematical update, okay, equation. You have W minus something. Okay, that something is typically the gradient descent. It's typically what? The minus what? You have the step size or learning rate, okay, and then the corresponding gradient. Okay, so this is gradient descent. So first of all, as I said, so you have to define the loss function. Okay, we did not talk about this last time, right? Have we talked about this? We have? We have a little bit. Okay, so we talk about the loss function. We have talked about the square loss, right? Okay, for the regression problem, you just use the square loss. And then for the classification, you can use, say, hinge loss. Okay, but then, so you say, for example, you can use the 0-1 loss, which is the easiest. But then, as I said, 0-1 loss, the gradient is typically 0 all the time, so it is not moving. And so instead of using the 0-1 loss, so you can use the hinge loss, okay? And then you will be able to have a non-zero gradient more often. Okay. But however, for deep networks, okay, so this is the gradient of the hinge loss that we discussed last week. Agree? But typically, or you can also try the logistic loss, okay, which is another kind of approximation of the 0-1 loss. Okay, and the advantage of the logistic loss is that it is smooth. But then, so for the 0-1 loss, but for neural networks, okay, so typically we use something else. Okay, so oftentimes we will use the so-called cross entropy loss. Okay, so what is this cross entropy loss? Let me see. I have forgotten to. So 1 second, I forgot to download the notes here. So do you find the file on canvas? The slide is there? Okay, good. Just download from canvas. No, it's not there. So let's take a 5-minute break. I have to go back to the office and do something. Okay, yeah. So first of all, we have to talk about information theory. Okay, so you can download the file at info.th.pdf. Okay, so what is information theory? So again, so we will first talk about entropy. So how many of you have learned about entropy? So basically, well, entropy is to measure the uncertainty, okay, or impurity. And so suppose that again we have two classes, and we have a set of samples. Yes, okay. So some of them are positive, some of them are negative, and then we have the corresponding probabilities for positive samples and negative samples. And so what that means is that this data set is not pure, right? We have uncertainty. In other words, if I draw a random sample, and then I'm not sure whether it will be positive or negative. Agree? So of course, the level of uncertainty depends on the p plus and p minus. So in the optimal case, well, when it's pure, okay, so when will it be pure? So this data set S, so when will it be pure? So I have a set of samples which can be positive and negative. It is not pure in general. Okay, it will be pure if what? So if either p plus, say for example, you can have if p plus is equal to 1, okay, or p plus is equal to 0, right? In that case, the data set S will be pure, and there is no uncertainty. Agree? And in the worst case, so what will happen? So when will I have least purity? So maximum uncertainty. So again, this data set S. So what will be the values of p plus and p minus? Then I will have maximum uncertainty. So when p plus is equal to 0.5, right? So 50% of the samples belong to the plus class, 50% of the samples belong to the minus class. Then when you randomly draw a sample, obviously you have no clue whether it will be positive or negative. Agree? And of course, if you are not that unlucky, you have a value which is, say, p plus is equal to 0.8, you still have uncertainty, but then you are not as uncertain as for the case where p plus is equal to 0.5. Agree? So that means that intuitively, if I want to measure uncertainty, so the x-axis is p plus, so of course p plus is equal to 1 minus p minus, okay, so that's the same. So if this is p plus, as I said, so when p plus is equal to 0, that means that you only have negative samples, you have 0 uncertainty. When p plus is equal to 1, you know that all the samples are positive, again, you have 0 uncertainty. But you have maximum uncertainty when it is 1/2. Okay? So intuitively, the measure of uncertainty will be a curve like this. Agree? So it then can be shown as well the entropy actually, as we will see later on, the entropy actually looks like this function. Okay? And so the formal definition, so we have a random variable x, okay, so we have you can take several distinct values, okay, discrete values, x1 to xn, and the corresponding probability is px equals to small x, and then the entropy is defined this way, okay, that means that you have the points, okay, and then you have px minus log px. Any questions? So how many of you have seen this equation before? How many of you have never seen this before? Okay, so basically, if you plot this out, so say for example, if you have only two classes, then that means that you have minus p plus log p plus and minus p minus log p minus. Okay, and of course P minus is equal to 1 minus P plus. Okay, so in fact this only involves one alone. Okay, which is either P plus or P minus. Okay, and so if you plot this out, you will get this curve. Okay, so that's why we argue that you can use entropy to measure the uncertainty. Okay, and then, yeah, so this is the equation when you have only two classes. Okay, and so of course you have px times log px. Okay, so px can be equal to 0, and so you can have 0 times log 0. Agree? So usually the convention is that 0 times log 0 is equal to 0. Okay. So here's an example. Suppose that again, as I said, you have a set of positive and negative examples. So 9 are positive, 5 are negative. So you plug in the equation. So the entropy is equal to, so P plus is equal to P plus. So for this example, P plus is equal to 9 over 14. P minus is equal to 5 over 14. Okay, so you just plug into the equation above. Okay, and so you will get this. And so here you have B. B is the base of the logarithm, and so usually we take base 2. Okay, and so you plug this in, and then you get a 0.94. Okay, so now the question is, does this make sense? So 0.94. So what is the worst case that you can get? So in this example, you have 9 positive, 5 negative. What would be the worst case when you have maximum uncertainty? When you have 7 positive, 7 negative. Okay, in that case, what will be the uncertainty? What will be the entropy? So that means that you have minus, in the worst case, you have minus 1/2, log 1/2, minus 1/2, log 1/2, right? And then base 2. So log 1/2 base 2 is equal to minus 1. Okay, so this is minus 1, minus 1. Okay, so this is equal to 1. Okay, so that means that in the worst case, uncertainty is 1. Okay, and so now for our example here, it is equal to 0.94. So does that make sense? Yes, because when you have 7 plus 7 negative, then you have maximum uncertainty. So now you have 9 plus 5 negative, so you are still uncertain, but you are a little bit better than the worst case. So you see that the entropy is equal to 0.94. Okay? And so of course, when all members, so all patterns in the S belong to the same class, then the entropy will be equal to, just like what we have seen before, it is equal to 0. Okay? And when you have an equal number, that will be equal to, so when you have two classes, it will be equal to 1. Okay? So otherwise, so when you have two classes, it will be between 0 and 1. Okay? So the more uncertain you are, then it will be closer to 1. Less uncertain, then it will be closer to 0. Okay? Maybe, so the TA has arrived, so maybe I leave the time to the TA. It will talk about the environment setup. Okay? And so that you can later on play with the Python or PyTorch packages. Any questions? Huh? The B is the base of the logarithm. So when you take the log, you have a base, right? So just like exponential, so the opposite is the exponential, right? Exponential, you can have a to the power x, right? So here's log to the power b. So we will talk about this in the next slide, okay? And we will continue about that next week. Okay, so any other questions? No? Good. Oh yeah, that's good. So you just set yourself up.
Okay, hello everyone. I am the TA of this course, and I'm Wei Chen. So today we'll first talk about the environment setup that will be very useful for the assignments of this course. So before the tutorial start, I want to take a very easy survey about how many of you have been used PyTorch or other like TensorFlow to train the machine learning model before. So seems that most of you have done before, right? So in this case, maybe in the later tutorials we will be more talk less about the basic training details. But but in this course I will cover the basic informations on how to set up the environment. So let's start with Anaconda. So here Anaconda is it can provide a general environment for tools for writing machine learning code, so such as Conda, JupyterLab, or Python, PyTorch, or many other useful tools. And you can download it from the official website, and you can choose the corresponding version, like Windows, Mac OS, or Linux. And Anaconda has two kinds of interface. The first one is the command line interface. So another one is graphical user interface. Though graphical user interface is very straightforward, but I recommend you to learn how to use command line interface. Of course, in the future, general, you will run the machine learning code on the server, which you cannot use command line graphical interface. So command line interface is most used for things. And so then we will talk about Conda. So Conda is a cross-platform package manager and environment management system. So let's first see what is environment. So here, environment is the directory that contains a specific collection of packages that you have installed. It's just like a box to collect all of the useful tools. And so why we need to do the environment management? So why not use a single environment and put all of the useful tools inside it? Because that we need to use multiple versions of a package. So for some project, maybe you can just maybe PyTorch 1.1 is enough. And for another project, you need to use PyTorch 2.7, which is the latest PyTorch. But if you use the same environment, then these two will conflict to each other. And another thing is that if you install a new package and this package might conflict with the previous package and it will automatically update the previous package, then your previous project cannot run correctly. So there is multiple conflicts between different environments. So when start with a new project, it is recommended to start a new environment. Okay, then let's see how to use Conda. So the first command is on how to create a Conda environment. So just use Conda create, and here -n, it means the name, and you can specify your name here. And after created, you still need to activate the environment to use it. So use the command Conda activate. Then if you don't want to use this current environment, we can use Conda deactivate. And sometimes you may forgot what kind of environment you have been created. Then you can use Conda info, then environments to get a list of all of the created environments. And here are also some commands for package management. So first is Conda list. So this views the list of packages and environments installed in the active environment. And also you can use Conda install to install package. But actually in general we can directly use pipe install, which is more easy to use. And also you can use Conda update to update some specific package, and use Conda uninstall to uninstall some package. And I just want to do a very simple introduction to Python. So this is very simple and elegant programming language, and it's just like human language. And we can see the programming code is much simpler than other programming languages before, like C, C++, or Java. So Python has been used in many areas, like data mining, machine learning, just like this. And here is some use for packages for different kinds of applications, like NumPy, Matplotlib, Seaborn, Pandas, SciPy, and sklearn. And you can also use the JupyterLab to run the Jupyter Notebook and do the interactive jobs inside the Jupyter Notebook. And this is the first part about the environment setup. And the second part is about how to find the computation resources. Of course, I think for the AI MSc course, you have been allocated the HKUSD support resources for your experiments, your projects, just like this. So I will briefly introduce how to use this. So here, HKUSD Superport is the state-of-art AI supercomputing facility in HKUSD. So it has very large number of GPUs. But its use is a bit different from the common servers. So you need to use the Slurm to submit a job. So you can check your email. You will receive the email titled HKSD Superport account created. Then you need to use any SSH client to log in to superpod.ust.hk. Then you can connect to the server. Then it will ask you to enter your name. So this is not your email address, just simple the things before the @ So your name, username. Then it will ask you to select the authentication method, and you can simply select the dual authentication method. And then after this, you successfully log into the server. Now let's see how to run the job on this server. So we will use the tool called Slurm. So this is a simple Linux utility for resource management. It serves as the business resource management and job scheduling system within this cluster. So it is mandatory for all jobs within the cluster to be executed through Slurm. And this is because that with this we can make a higher utility of the whole computing resources. When someone needs to run, it will be joining the queue, then it will be assigned some computing resources when the resources are available. So in this case, all of the GPU are in expectation, so all GPU will be running all the time. None of them will be idle. So let's see how to write the code. So this is just a simple code for testing. So it's very easy. Slurm testing code doing the dot product of the two matrix. Okay, let's see how to write the S-batch code. So at the beginning, we will have some S-batch parameters. So the job name means you can just use a name for identification your job, and how many nodes you need to use. So here, usually one node means there has 8 GPUs. So usually you just need one node. Okay. Then how many GPUs you need to use, and what's the maximum runtime, and what's the partition. Usually it has different kinds of partitions, such as large, normal CPU. Then it depends on your usage. You should submit your job to the correct partition. And then finally, the account. This is the Slurm account in your email. And then we need to load some modules that will be used, and then you can run your code. So after writing this test.sbatch, you can then use sbatch. Then this is the test.sbatch to run your code, and you can see your output in the slurm.out. And another very useful command is the interactive job. Of course, in the previous command, you cannot build interactive job. If the job crashed, you need to join the queue again, then run it again, wait for a long time. So if you want to debug or you just want to do some interactive job, you can use this command called srun. The other parameters are very similar to before, just like the nodes and GPUs per nodes, just like this. And you can specify the time here. And after running this code, if your job has been assigned the resources, then you can directly use it as in the common GPU server. Okay, that's all of today's tutorial. Any problems? Any questions? No, then that's all for this tutorial. Thank you very much.